Cool, thank you, Anna. Up next, we've got Danny Lim.
Hi, this is Danny Lim. I'm a first year graduate student in Thomas Lab at UCSB. Uh, Slide, please. Yeah, so spatial working memory is a temporal storage of visual spatial information that guide behaviors. The big question for us was, how does the context of local environment shape what we remember about space? More specifically, we were interested in whether simple geometric cues like the shape of the visual boundary can systematically bias where people think a remembered target was. Past work has shown that spatial working memory isn't always precise. People's gaze or pointing often drift towards certain default direction or midpoints, and these aren't random. They seem to reflect internal biases or heuristics. But less is known about how external geometry, the context, might shape these biases. So we asked, does the shape of the viewing aperture, like a square or a circle, systematically distort spatial memory? Slide, please. Think of how some people rotate their monitor vertically while others keep them in a wide horizontal format. Even though the content stays the same, the spatial frame changes, and the simple shift might influence how locations are held in memory. To test this, we use a simple memory guide as a Saccade task. Each trial followed the sequence shown here. Participants briefly saw a target dot inside one of four randomly assigned apertures: a circle, square, wide rectangle, or tall rectangle. After a short delay, they made a Saccade to where they remembered the target being. We recorded the final eye positions and compared to the true target locations to measure a spatial recall error. We recruited 10 participants and the experiment followed a within subject design. And we randomized a full set of 64 trials as a unit composed of 4 different aperture shapes crossed with 16 target dot locations, which were evenly spaced across 360 degrees to ensure full spatial coverage. Okay, next slide. Yeah, as mentioned earlier, we measure saccadic endpoints. Here's an example of showing the distribution of saccade endpoints for the circle aperture conditions. From this data, we also computed the average recall error at each target positions within each aperture. Looking at overall error shown in the bottom left plot, it didn't differ significantly across conditions. So on average, participants were equally accurate regardless of aperture shape. While there were no main effect of conditions, the interaction term between aperture shape and target positions was statistically significant. To explore this, we visualized how errors were distributed within each condition, shown in the upper right plot. There were distinct systematic patterns that varied with aperture shape. This was especially clear when comparing the wide and tall rectangle. In the wide rectangle, the error skewed horizontally. In the tall rectangle, they tended to skew vertically. Error magnitude was modulated by aperture shape with larger deviation along the aperture's elongated axis. This suggests that spatial recall is not shaped solely by the internal memory process. It is also reliably biased by the geometry of the surrounding visual context. We're now working on modeling these biases more precisely, for example, by examining how error varies as a function of distance from aperture boundaries and etc. Slide, please. So the main takeaway is that working memory recall is biased by the local visual environment. And as a next step, we're testing whether these biases persist with non-ocular motor response, like mouse clicks. Thank you.